Hey everyone. Today we're going to talk about a specific kind of problem that we call static equilibrium problems. And to understand what a static equilibrium problem is, let's take a look at the words themselves. So static means not moving. You may remember from an earlier video we talked about static friction, right? Well, same word, similar application. Static means not moving, stopped. All right. Equilibrium means balanced. And specifically in this case, it means balanced forces. So a static equilibrium problem is one where an object is not moving because its forces are balanced. And these problems are incredibly important. Specifically, you see this a lot in civil engineering, and that's what my background is in. Um, Because what is the goal for a building or a road or a bridge? Not to move. And so in these problems, we're basically taking forces and figuring out what do they need to be so that we are not going to move anywhere. In this video, I'm going to look at kind of three levels of problems, and we're going to walk through three examples and see how that works. And then I will say that, these can get basically as hard as you want them to. I'm going to try to look at kind of three things that might make a little difference. Um, but I will talk at the end a little bit about how, especially if you're looking at this not as an introductory physics student, but maybe as like a first year engineering student, what are some of the ways that these can get a little bit more complex, and some guidance for you there. So we're going to start with truly the most straightforward of these that I can think of. We have a box, and on that box we have three forces. Two of these forces we know, and one of them is unknown. So let's say we have a force of 300 newtons to the right, a force of 400 newtons down, and here some unknown force F. And our goal is going to be to figure out what that unknown force is, so that the object, the box, will not move. So the first thing we need to do, and I've got up here for you kind of my 1, 2, 3 guide to like how to solve these problems. The first thing we need to do is break up any diagonal things into horizontal or vertical. So here we've got fx and fy. In other words, this diagonal force that we're pulling to the left and up, well, we could replace that, right, with a force that's just to the left and a force that's just up. And our question would be, how big do those need to be? And this is a really important idea in all of physics and engineering. The idea that horizontal things happen separately from vertical things, and vertical things happen separately to horizontal things. I always think of the example of like, if I walked up to a chair and pushed down on it really hard, you would be shocked if it flew out to the side. You might expect it to go down, but to have horizontal motion from a vertical force is not something you would expect. And that's because horizontal and vertical things happen very separately. And so the key to two-dimensional physics, all of two-dimensional physics and three-dimensional, for the record, is just to understand that you can separate things into horizontal and vertical and solve them separately. And that when you recombine them at the end, which is kind of part of this last step, recombining if necessary, that it will still be the right answer. So let's move to our next step, that net force equals 0 step. Here, what we're going to do is we're going to set up that the net force in the x direction is 0 and that the net force in the y direction is 0. Why? Because if it's not moving, it's not accelerating. And if it's not accelerating, aka it has an acceleration of 0, then net force equals ma. Well, that suddenly becomes net force equals 0. And again, to make our life easier, we're going to do this separately in the x direction and the y direction. So let's take a look at all of the vertical forces we have going on. We have Fy, which is pointing upwards over here. So I'm going to make that positive. And then I also have this 400 Newton force down here that's negative. So minus 400. And what I know is that Fy minus 400 has to equal 0. Now, what does this tell me? Well, it's pretty straightforward in this case. It tells me that Fy equals 400. All right. What about Fx? We can do the same thing, except here, our Fx isn't positive. So let's go look at our positive forces. First, we have 300 Newtons positive minus Fx equals 0. So Fx equals 300 Newtons. Now, what I might need to do at this point is actually answer the question I was given, which was, how big is F? And I don't quite have that yet, right? I have the two sides, but I don't actually have that unknown hypotenuse. But if you remember from our right triangle video, which I'll link that here, we can just do Pythagorean theorem. 300 squared plus 400 squared equals c squared. And in this case, it does happen to be a special triangle. We'll get c is 500. So 345 times 100. And so we get 500 newtons. Now, you might also be asked at some point to find maybe the direction, say this angle. And I'm going to point out here that it's pretty straightforward to do. I'm also going to point out this is my introductory version of these problems. And so after this point, I'm not going to do this again. But what you really need to do is acknowledge that the tangent of theta is opposite over adjacent, 400 over 300. And so what you'll do is you'll do an inverse tangent where you tell your calculator what the tangent is, and it tells you what the angle is. And so if we do the inverse tangent of 400 over 300, you'll get an angle of 53.1 degrees. And that would be that angle. And so for any of these problems, if you're asked to find an angle, just remember to do an arctan, an arcsine, an arccosine, otherwise known as an inverse tangent, inverse cosine, inverse sine, in order to do it. All right, let's take a step up. What if one of those forces that we know was also at an angle? So let's say I have a 100 Newton force down and a 100 Newton force here at an angle of 45 degrees to the horizontal. And I want to know, well, what force do I need over here to balance it all out? Some of you might look at this and actually have some ideas based on symmetry, and I think there are probably some pretty good ideas, but let's go ahead and solve the problem and see. You may remember our first step is to break up any unknowns, any diagonals into x's and y's. And in this case, it's a little interesting because we don't just have our fx and fy, we also have what I'm going to call for the time being x and y, the two legs of this known force that's at an angle. And so what we need to do before we can even start on the problem, before we can worry about finding fx and fy and f, is find x and y. And we're going to do some trigonometry for that. So if we think about the sine of 45 degrees, it's going to be opposite over hypotenuse. Opposite is y, hypotenuse is 100. And we will get y equals 100 times the sine of 45 degrees. And so when we type that into our calculator, we will end up with 70.7. And it is 70.7 newtons, to be clear, because this was newtons here. And we'll do the cosine of 45 degrees is adjacent over 100, x over 100. So x equals 100 times the cosine of 45 degrees, which is 70.7 newtons. This is when I talk about this in an introductory physics class where I say, please remember, please, that angles do weird things. So a lot of people get freaked out when they realize that these are the same number. It's actually a pretty well-known trait of 45-degree angles. In fact, if we think a little bit more deeply about this triangle, that's a 45, 45, 90 triangle. It's an isosceles triangle. So it is going to have the short legs, the same length, and then a hypotenuse. But a lot of people get kind of freaked out right away, and they don't even think about wondering if that might just be how it works. In our last problem, we'll also look at an example of angles do weird things. So please don't get freaked out by angles that are doing things you don't think angles should do. So now we have everything broken down. We can do our net force in the x direction equals 0 and net force in the y direction equals 0. In the x direction, what do we have going on? We have little x, which is 70.7 newtons, and that's positive, minus fx, and nothing else, so equals 0. So fx is 70.7 newtons, and it is to the left. By the way, if you ever solve one of these problems and you get a negative there at the end, what that means is that you made an assumption about what direction the force should be in, and it was wrong. So it's just the opposite. So if I had gotten negative 70.7 here, it would tell me that this force needs to be to the right. But I didn't, so it doesn't. In the y direction, we have a little bit more going on. We have Fy pointing up. We have 70.7 pointing up. And we have 100 pointing down. And so if we, that's weird. If we go ahead and do our math, we get Fy equals 29.3 newtons. And so we could come over here and have 29.3. And then it's just a matter of 29.3 squared plus 70.7 squared equals some very large number, but we're going to get an answer here of about 76.4 for F when we use the Pythagorean theorem. All right. And again, if you wanted to, or if your teacher asked you to, you could find this angle using an inverse sine, inverse cosine, or inverse tangent. I'm not going to do that here. Last level, level 3. This is where basically they're all at angles. So let's take a look. Maybe this one is, I'll stick with 100. It makes my math a little easier. Let's do this one is at 100. And then we're going to have some F out here. And let's make those a 30-degree angle and a 60-degree angle. All right. First step, as always, is to break this up into verticals and horizontals. I do like to color code these, as you may have noticed. All right. And now we're looking here then for x1, x2, and f of x, as well as y1, y2, and fy. So if we look at our 60-degree, we're going to have that y1 equals 100 times the sine of 60, which is 86.6 newtons. And x1 equals 100 times the cosine of 60, which is 50 newtons. Over on this triangle, we're going to have 100 times, well, y2 is 100 times the sine of 30 degrees, which is going to be 50 newtons. And x2 is 100 times the cosine of 30 degrees, which is 86.6 newtons. Now, in another edition of Angles Do Weird Things, you may notice that these are like flip-flops of each other, right? That like the x from one is the y for the other. They're inverted. That is actually because these angles add up to 90 degrees. That is a fairly well-known feature, again, of angles. But if you didn't know that, you might freak out. So again, angles do weird things. Try not to freak out. Let's do our net forces in the x direction add up to 0. And our net forces in the y direction add up to 0. All right, in the x direction, we've got x2 is positive, so 86.6. And then we have 50 is negative and fx is negative, and they're all going to add up to 0, which means that fx is going to be 36.6 newtons. In y, we've got both y1 and y2 are positive. So we've got 86.6 newtons plus 50 newtons minus fy, and fy is 136.6 newtons. And again, if we're asking to find x or f, then we're just going to need to square those, add them together, and you'll get f is 141.4 newtons. Now, I said at the end I would talk a little bit about how these could be harder, and how you might best adapt to that. So first of all, I want to say that, we've only done 3 forces on all of those problems, and you could have a lot more than 3 forces. So you could have 5 or 8 or however many things you can put in there. And so that's one way that it gets kind of more complicated, but not necessarily actually harder. You would do the same thing. You'd still break everything down that's not already a horizontal or a vertical, And then you're going to add all your horizontals, add all your verticals, and go about your business. You could have a three-dimensional problem. So you could have forces in and out of the board as well as up and down and left and right. Um, and then the other like big thing that gets added later on, especially for civil engineers, is torque. So what if you're trying to twist it as well as move it? That adds a whole extra layer, and that's when it gets not just more complicated, but actually like truly more complex. And so we'll see, maybe for my AP students, I will go ahead and throw on another video here that takes it to that next level. But thanks so much. Have a great day.